morning, guys. Today we're going to go over 4.9 or graphing polynomials. Now, normally, previously when we were graphing, we used to use tables in order to find x's and y's and plot along the coordinate plane. And that's how we get our graph. Today we're going to learn a different way to graph a polynomial. And even though it's not going to get you a perfect graph, it's going to get you a good approximation of what it looks like. In order to graph these polynomials in this certain fashion, we're going to have to focus on the x-intercepts. We're also going to be combining the concept of x-intercepts and end behavior in order to do this basic graph. And we're also going to learn a new theoretical concept called turning points. Now let's look at a particular example. Let's say they give me this polynomial. X minus 3 squared. Again, they're giving it to me in factored form. They're giving me x minus 3 squared as a factor, x plus 2 as a factor. Now, given these factors, I can find my x-intercepts or my solutions. The x-intercepts would be the numbers that you plug in here to get 0. So positive 3 would be an x-intercept or solution. Also negative 2 would be another x-intercept or solution. So the trick is the following. Once you have your axis, you label your points. Positive 3 and negative 2. And you put 2 dots on top of your coordinate plane or a little line where they correspond. Now the next trick is, let's use end behavior. Remember, end behavior is how my x or how my y behaves as my x approaches positive infinity and my x approaches negative infinity. And I get my end behavior based on the degree of the polynomial. In order to find the degree, when they're giving it to me in factored form, you have to see how many x's you have pretty much. So here I'd end up with 2 x's, and when I add this one, I would have a third degree polynomial. If you were to multiply these two polynomials, you'd end up with x cubed and a whole bunch of other things. But remember, end behavior is based solely on the leading term's degree. So now that I know that this polynomial is of third degree, remember, a third degree polynomial looks something like this. When it's not reflected, and this one isn't, I always begin on the lower left-hand side, so you put a dot here, and I end at the upper right-hand side, so you put a dot here. And the whole point of end behavior is correctly placing the dots so you can then connect them. Now we have to connect the dots, but I do have to pass through all my x-intercepts. I have to pass. I can't just connect the dots like this. I have to go through both negative 2 and positive 3. Now, how do I proceed? It's pretty straightforward. All you have to do is look at the degree of each factor that you're given, and it's very important. Why is it important? Pretty simple. Let's take the negative 2, for example. Belongs to this factor. I look at the degree of that factor. Since I'm not given a number, I know that degree is a first degree. Whenever your degrees are odd, you go through that 0. I go through that 0. You pass through that 0. Now let's look at the positive 3. The positive 3 is of second degree. When you touch an even 0, you touch it and bounce back. So pretty much the polynomial would look something like this. I bounce and I go up. If you graph this in your calculator, you'll get something like this. Now the only thing that you can't do is know how high this will go or how low it will go sometimes. You just do a normal curve and continue. The important part of this graph are the zeros that have to be properly labeled, the end behavior that has to be properly placed, and also if it bounces or goes through. Let's look at another example. This time, more complicated. X plus 5 to the 5th, x minus 3 to the 4th, x plus 2 to the 2nd, x minus 1. Oh my God, not that difficult. First of all, again, step 1, our axis. Step 2, let's place your zeros. Let's say this is -5, this is +3, this is -2, and this is a +1 over here on this side. Again, -5, +3, -2, +1. I placed my zeros correctly. Now let's go over end behavior. 5 plus 4 is 9, 10, 11, and the one more is 12. So when you have an even leading term, we have something that looks like a parabola. So I would begin on the upper left-hand side and I end on the upper right-hand side. So I'm going to begin here, I'm going to be touching all my x's, and I should end up here. So let's see. The first zero I come across is this one. Since -5 has an odd degree, I go through it and I continue. Now, the second zero that I see here is not always the second term. So you have to be very careful. You have to look at the term you're working with. So -2 is this one. Since this one has an even degree, it's gonna touch it, but bounce like a ball. It's gonna bounce. It bounced. It touched the x-axis and bounce. Now I'm gonna reach the +1, which is this one. Since it is an odd degree, it's gonna go through. And then I'm gonna reach my 3, which is an even degree. It's going to bounce, and you will see there is no way, if you do the bouncing or goes through correctly, that you will not end up as your end behavior states. So again, odd degree, I go through the x-axis, but I do touch the 0. Even degree, like the 3, I touch the x-axis and bounce off. Again, it doesn't matter how low you go here, how low you go here, how high you go here. Just make a nice curve. Don't worry about it. So if you go this high or this high, it's not going to be wrong. Just don't go crazy. There is no need to do this. Even though if you want to do it, that's fine. There's no need to do that. Again, bouncing and going through. Now the last term or the last theoretical concept we're going to learn today, we've already gone over, I believe, not sure, but we're going to go over the concept of local maximums and local minimums, or turning points. Turning points are points where the behavior goes from increasing to decreasing. Okay? From increasing to decreasing. That's a turning point. Now, yeah, I believe we went over this when we went over the parabolas. Remember the local relative maximums, relative minimums, absolute maximums, and absolute minimums. Let's say, for example, I have a parabola. I know that I have this curve and my two ends are going infinitely upward. Since there is no point below this point on the graph, my graph does not exist at any point below this point, the vertex, that is considered an absolute minimum because there is no, my graph does not exist, so it's not part of the range under that particular point. So that's an absolute maximum, a minimum. Now, if I were to go like this, for example, this here is a turning point because I'm going from decreasing to increasing. But since my graph exists below that point, it is not an absolute minimum, It is a local minimum. All right. The same applies for maximums. If it's a parabola, that would be an absolute maximum. This would be a local maximum because my graph exists above this point. Look over here on this side. It exists. So pretty much if your functions are even, like a parabola, they will have absolute maximums or absolute minimums. You can also mix and match. This polynomial has a local maximum, an absolute maximum, and a local minimum. So you can mix and match. Odd functions, which look something like this, cannot have absolute maximums or odd polynomials, cannot have absolute maximums or minimums because they always extend infinitely upward and downward. There is no end. It's not like your parabolas that have a turning point and then they go in the same direction where they came from. Okay, that's pretty much it for today's class. So go ahead and graph exercises 7 through 12 in this fashion. Remember, the fact that they put fractions in front of your factors makes no difference. Doesn't matter. Coordinate, find the zeros, list your end behavior, and then bounce and go through and you're done. So for homework, please do 7 through 12. If you have any questions, please ask in the class answer question forum. Have a great day, guys. Bye-bye.